Now for something a little different. So Vincenzo Cirigliano is an expert in issues regarding neutrinos and quantum field theory and particle astrophysics in the early universe and electroweak baryogenesis. But of late, he's been working on quantum kinetic equations, and he's going to tell us about that in a series of lectures.
Okay. All right. Well, can you hear me? Okay. Thanks, George, for the nice introduction and the invitation. So I'll talk about neutrino quantum kinetic equation. You've seen versions of the QKEs already in this school. I looked at the program. I'm going to present an approach that we developed with George and Alexei Vlasenko here, and it's based on these 3 papers. These are the references, and I apologize in advance to all the other authors that we refer to, but you can look at these references and reconstruct the earlier literature. So this is dying.
Try the other laser pointing.
Okay. Oh, great. Yeah. Sorry. All right. So here's the outline of. So I'm scheduled to talk today and tomorrow. Roughly speaking, today I would like to go over motivation, basically coming from neutrino and the role they play in cosmology and astrophysics. I then go over and describe neutrino. How do we even, from first principle, try to describe neutrinos in a hot and dense medium, all right? So we have to use the density matrix or something similar to that. And then my goal is to finish up today by giving to you a little bit of a flavor how to derive the QKEs from quantum field theory and look at the structure. We stare at the structures of these equations. Then tomorrow we'll go into a little more detail and look at the anatomy of the QKEs, look at each term, the physical meaning of each term. In particular, we'll see coherent evolution both with flavor and spin degrees of freedoms that are often neglected. And then what's the role, how do we take into account of inelastic collision, like scattering process, inelastic scattering. And then I'll conclude with a few words of comparison with other approaches and future challenges that, in my opinion, are partly analytic in terms of understanding, but mostly computational. And that's how probably this talk fits into this school. And then there will be a talk by Alexei Vlasenko, who will describe early exploratory study of the role of neutrino and antineutrino transformation in astrophysical, in compact objects, basically. All right, so the emphasis I'll try to give is more on the physical meaning of objects. So if you are interested in the formal details, look at the papers. They're but my hope is by the end of the lectures to demystify this topic. This looks like a very cryptic argument. I'd like you to have a good, sound physical understanding of what these QKEs are, all right? And maybe the details, we won't go into much detail, but that's my goal. All right, so by now, this is, okay, you know all about this, but let me start again just on a short introduction of neutrinos. These are a very elusive particle and fascinating particle. They're the lightest fermions. Their masses are 6 orders of magnitude at least smaller than the electron mass. They only feel the weak force. They display this very interesting feature, which is that the interaction state, the flavor states, which are nu e, nu mu, and nu tau, do not coincide with the mass states. So now I have just a question for you. How do we know, what's our practical definition of the flavor state? What's a nu e, as opposed to nu 1, nu 2, the mass eigenstate nu 1, nu 2, and nu 3?
It interacts via the charge current interaction.
Exactly. So whenever you, let's say, absorb an electron, you say you, in a weak process, you produce a nu e. Or whenever in a weak decay you produce a positron, you've also produced a nu e, right? And how do we know when we say it oscillates? How do we know now we have measured a nu mu? It's very similar. When you see a muon coming from this detection reaction, you say that the nu mu has had that interaction. So that's the meaning of this. So So as a consequence of quantum mechanics, a neutrino produced in a given flavor state, as we said, can oscillate into another through this interference. And as you see, so the amplitude of oscillation, this is the survival probability. Let's say if it's produced as a neutrino of type alpha, the survival probability oscillates with amplitude dictated by the mixing angle here, and oscillation length dictated by basically energy over the mass square difference, all right? And this is the this is survival. This is a creation probability of the other flavor, obviously. The total probability is 1. Now, hope this puts all back on the same page. Despite this, the elusive nature and this mysterious nature, neutrinos play a key role in cosmology and astrophysics. And there's basically 2 questions that drive the need of writing down these quantum kinetic equations. And I'm going to go over these 2 key issues. There's an underlying unified picture underneath, and I'll tell you about it later. So, but the 2 questions I have in mind that motivate me to do this work is that go back to the early universe, right? Very early, the neutrinos are in thermal equilibrium, thermally coupled to the plasma. At some point, they decouple, right? And my question, the question we want to ask is, what is the spectrum and what's the flavor content of the neutrino thermal bath when they decouple in the early universe? Answering this question is important because both these quantities, the spectrum and the spectral and the flavor content, they are key input in the calculation for, as you've heard, of Big Bang nucleosynthesis. Because, and the point here is illustrated in this cartoon, between the neutrino decoupling and the weak freeze out, where basically the neutron to proton ratio is set, there's still 10 to the 10 neutrinos per baryon, and they participate in these weak processes that interconvert neutron and proton. And obviously, these weak processes are flavor dependent. They select the neutrino, the nu E flavor, and they're strongly energy dependent. So you want to know something about, want to know as precisely as possible the spectrum, all right? And then, of course, once you've set this, and after weak freeze out, then the network of nuclear reaction kicks in, and you get BBN. So this is question number 1. Question number, yeah, let me elaborate on that. The idea is that now this is very exciting because we're going to have ever more precise observation of, from cosmology, of the baryon density and the energy density of relativistic degrees of freedom, the primordial abundances of light elements. So once we couple that to robust theory, we can turn BBN into really a probe of physics beyond the standard model, in the sense that we can start playing, adding sterile neutrinos, adding non-zero total lepton number in the universe, and so on. I mean, this, to some extent, all this is already being done, but the question is, how robust is the theory behind this? And you've heard lectures about the nuclear reaction networks. Here, we are going to try to set up the tools to get the right neutrino part, the spectrum and flavor content. The other application that we have in mind, and again, you've heard about this earlier at this school, is it has to do with neutrino emitted by compact objects, or supernovae. In particular, we have, so what you've seen probably so far is the treatment, it's based on a separation of regime. People usually say, okay, inside the core, there's a critical density that divides the neutrinosphere from, divide the inner core from the envelope. And basically, in the calculation of collective neutrino effect, you take as a boundary condition, initial condition here, neutrino emitted with a given spectrum in all possible angle, I mean, a given spectral and angular distribution, and then you let them free stream. And then they, of course, intersect. It's a many-body problem because they intersect each other, their flavor evolution is coupled, and so on. Now, the question it's been asked already by JJ, Joe, Alex Friedland, George Fuller, and Alexei Vasenko was, what's the impact of inelastic scattering? Okay, we know that at some level, even if the density, so this cartoon, this plot shows the density, typical density profile from a two-dimensional supernova model. Even though the density decreases out here in what we call the envelope part, some neutrinos will scatter. And in fact, JJ computed that essentially less than 1% of the neutrinos scatters. But there's a huge impact on the flavor potential that the other neutrino sees because of the different angular dependence. These are, once a neutrino has an inelastic scattering, it intersects other neutrino trajectory at a large angle. And since the potential neutrino-neutrino induced potential goes like 1 minus the cosine of the intersection angle, this could be a large effect. Even a small fraction of neutrino scatter, but with a large angle, it does have a big impact. And this was already shown by JJ and collaborators. So that's the idea. We want to put these two things together, the coherent evolution and the incoherent effects due to inelastic scattering. So this is again saying the same things. Both in the early universe and its compact objects, most state-of-the-art calculation, they do separate regimes. They say there's a high density, high temperature regime where the neutrinos are in equilibrium. Then after that, they free stream. What happens in between, that's not very well understood, both theoretically and computationally. And that's the goal of the QKEs, right? We want to understand both coherent flavor oscillation and the coherent inelastic collisions, okay, with the medium. How do we go about this? How do we do this? We have to go back to quantum mechanics and remember, so how do we describe a thermal bath? Probably the early example that you've heard about in quantum mechanics, thermal bath of spin one, two-level systems, right? A spin 1/2 or two-level molecular or atomic system, right? The idea is you describe this through the so-called density matrix. You describe an incoherent, the system, the ensemble, by an incoherent mixture of states. Let me label them by K, which each one of them carries some weight, P sub K, a probability, all right? So if I have a pure state, there will be P sub K will be 1, and I only have one state, and that describes my system. In general, where you have incomplete knowledge of the system, like in a thermal bath, you define this density operator, which is sum over the states in the system weighted by their probability, P sub K, and then you have this projector onto that state, all right? And the density matrix from quantum mechanics, this is quantum mechanics, evolves, if you know the Hamiltonian of the system, evolves according to this equation. And let me give you some example. I mean, the example of the density matrix associated with a thermal equilibrium ensemble, is given by this. There's a normalization factor down here, the trace, and then it's basically the Boltzmann factor, e to the minus h is the Hamiltonian, divided by kt. So the P sub k for the energy eigenvalues, eigenstates, P sub k is e to the minus e sub k over kt. And then downstairs you have the sum, the partition function. All right, this is an example of thermal equilibrium. So how does rho, the density matrix, control the dynamics of the system? Because of the following thing. If you get any operator associated to any observable, the ensemble average of O is given in general by this sum again with a weighted sum of the average of O over each k, which becomes trace of rho with the operator. Now, all this is just a review of what we do normally in quantum mechanics. So for neutrinos in the environments we want to study, what's the relevant O? Which operator we want to track? What are the questions that we want to ask? Well, typically in early universe and supernova, we want to extract, things that affect the dynamics and then can be eventually even observable, like a neutrinos signal on Earth from a supernova. They involve neutrino densities and fluxes, right? That's what we want for what alpha is electron mu tau or possibly sterile state. So we need to deal with some sort of a generalized number of operators. So if you want the electron neutrino flux, you have to know something about NEE, which has to do with where the generalized operator are defined in terms of the creation and annihilation operators of one particle states, where I and J label really all the quantum numbers that you can assign to one particle state, according to this. All right? So, and then already at this stage, one thing you can say, if you're interested in the neutrino density, right, NEE, the electron neutrino density, say, wow, what do I care about flavor? The point is that the dynamics couples all the NEE. any E to any mu and then E tau and so on. So that's why we need to write kinetic equations that couple the ensemble averages of all these operators consistently. So, let's now go, this is the big picture, let's go into a little more detail. What is really this label I and J? How do we label one particle states for neutrinos? So we describe neutrinos by massive spin-1/2 fields. So the labels are in principle, so you can write a neutrino state as a creation operator labeled by the 3 momentum P, the mass. If I work in the mass basis, it's the most natural basis to work with. It's the mass of the state I, m sub I, if I have more neutrinos. And then I also have the spin degrees of freedom. I have to attach the spin quantum number, and it's very convenient for our purposes to use the helicity, this projection of the spin along the momentum. That's what helicity is. So a left-handed particle is moving this way, momentum is this way, the spin is projected the opposite way, it points opposite to the momentum. A right-handed particle is the other way around. The spin is aligned to the 3 momentum, all right? So this is familiar, right? Am I using terminology that's you're not familiar with? So if the and the same you can do with the antiparticle. Now, if the neutrino is a Dirac, is described by Dirac field, then you have 4 states. You have left and right-handed, so the 2 helicity component for the neutrino and the antineutrino, exactly like the electron. So in the Dirac case, the neutrino is just a electrically neutral and lighter brother of the electron. But other than that, in terms of counting states, it's exactly the same as the electron. If the neutrino is described by a Majorana field, if you use this fact that a neutrino is electrically neutral, and in principle it can be described by something different than a Dirac field, which is called the Majorana field, then you only have 2 states, which we label left and right-handed neutrino. I mean, we say that the neutrino is, the antineutrino is the same as the neutrino, but the underlying condition in the field theory is that the spinor field is self-conjugate. If you take the charge conjugate, it's equal to itself, or equivalently, you can choose the phases so that A and B, the creation operator, are the same, coincide. All right, so this is, we're going to come back to this. It's kind of keep it in the back of your mind, this idea that the physics could be slightly different for Dirac and Majorana neutrinos. So now, so this is probably this set of slides is the most important set of slides for today's lecture. So the key dynamical quantities, as I said, are these generalized number operators. So, and ensemble average of, let's say, and let's walk through it. Okay, so in the case of neutrinos, I'm going to now do A dagger A, and I put all the labels, so momentum P prime, J is the mass or flavor, let's stick to the mass for now, and helicity, H prime. And then I correlate it with A of mass I, helicity H, and momentum P, right? What does it, and of course the A, they satisfy canonical anti-commutation relation, and the omega is the usual free field P squared plus square root of P squared plus Mi squared. What can this be equal to? Well, there's a bunch of normalization. These are essentially conventional, the normalization. The non-trivial physics comes here. There's a delta function of momentum, of 3 momentum. This comes because we are assuming that things are nearly on the wavelength of, on the de Broglie wavelength of the neutrino, things are smooth. The background is very smooth. Even though they're in a supernova or in an expanding universe, those external gradients vary much more slowly on the scale, much slowly on the scale of the neutrino de Broglie wavelength. So you basically have on a microscopic scale, you have homogeneity, basically, and that's a 3 momentum conservation. And then there's a function. This is the dynamical function, which I call, Raffelt, I think, originally called it the matrix of densities. So carries, again, labels. I mean, it carries the argument P, because we're correlating, and carries a bunch of labels. Ij from the mass, these are the modes creating or annihilating mass I and mass J neutrino, and the helicity. I could create it left or right, right? So that's why it's a matrix, okay, carries these indices. So you can do this, and then you can do the same for anti-neutrino, and the anti-neutrino matrix of densities, I label with F bar, all right? Again, nothing. So what's the physical meaning now? What's the physical content of these objects? So these are the objects that we want to know. If you know these, you realize, right, we know a great deal about the neutrino. I can compute the nu E flux, the nu E energy density, and so on, stuff that are important then in BBN reactions, in supernova, nucleosynthesis, and so on. So let's look at this is a matrix. Let's look at the diagonal components, II, HH. Let's say F11 and left LL, left. This represents the occupation number of a neutrino of mass m sub I, helicity h, and momentum p. This is really the standard case from quantum mechanics. This is the number operator of the harmonic oscillator. There's nothing fancy. It's the dagger times itself. So that's now, and that's the occupation number, right? So that's all you have in the one flavor case, right? That's all you have. Now let's ask ourselves, what is the physical content of the off diagonal? And let's do this so there's several ways that we can go off diagonal. Let's keep h prime equal to h, right? And ask ourselves, what's the physical content of the off diagonal when I equal 1, let's say, and j equal 2. So can you guess what would be if I have F12 left non-zero? What's the physical meaning of that? So obviously it's going to tell me something about this ensemble average. Remember, there's a trace over the density, an incoherent sum over the states, right? That are in the system. So what's the condition that I need in order to have F12 different from 0? Non-zero mixing angle is not quite, I mean, you need that, of course, but well, you're on the right track. Coherence, exact. So the right thing is coherent. So the right answer is coherent. Of course, the way you get coherence is if you have a non-zero mixing angle, and we go back to our original discussion, how you put the thermal bath contains a nu E, a flavor state. What is a flavor state? It's a linear superposition of nu1 and nu2 in the two flavor case with coefficient given by cosine theta and sine theta. Of course, that's how you need a non-zero mixing angle. Okay, so this is what I wrote here. So Fij HH with same helicity signal quantum coherence between states of same helicity and different mass. So this can be non-zero if there are states in the ensemble. This is I'm repeating just what we just said. Non-zero if there are states in the ensemble that are coherent superposition of states of same helicity and different mass. For example, the neutrino flavor state. This is exactly this example. So you have nu alpha is cos theta sine theta. If there's one of the p sub k, the weight, there's a non-zero weight for the state, the ensemble to contain nu alpha, then if you work out the meaning of this ensemble average, you get that F12 is proportional to sine theta and cos theta, the two coefficients of the linear superposition of 1 and 2. Okay, good. So if you understand this, basically you understand most of what I'm going to say. So this is a crucial point. If you have doubts, please ask. Yeah.
Can you explain again why you need coherence for that term to exist?
Yeah, so let's go back for a moment to the definition of this bracket, the ensemble average, right? So what's the definition of ensemble average? It's given, here. So remember, we are defining, so go back here and say, suppose I have a beam of nu alpha, or nu E, let's say, okay? How would I describe, what's the density matrix for that kind of system? It would be just one state, and suppose I also know that this beam is monochromatic. There's only, there's a wave packet, okay? So there would be some weight here. So the state would be the K would be labeled by flavor E, just one flavor. and maybe a distribution of momenta, okay? And that would be taken care of by the P sub k, all right? Then, remember, I have to compute now A dagger A. Now, O, I have to stick here A dagger 1, A2, all right? Which means, okay, I get some little weight from the wave packet. Then I have to take A dagger 1, A2 in the flavor state alpha. Remember, if I had a board, it would be much easier. But the idea is, look at this formula, this term here, and stick in here A dagger 1, A2, all right? And remember that K is cosine theta times state 1 plus sine theta state 2, all right? So if I only have K equal 1, 1, so the diagonal term with K equal 1 and 1, it's of course 0. A dagger 1, A2 gives me 0. These are annihilation operate. I mean, if you can carry to the vacuum and then it destroys the vacuum, it gives you 0, right? So the other thing to keep in mind, you have to remember, right, that the neutrino with quantum numbers I is written as this mode operator, A dagger I, acting on the vacuum, right? So is this clear enough? That if I have A dagger 1, A2, and then acting on a state where K is 1, 1, I get 0?
But I thought you were saying that you would get 0 if it was, only if it was coherent. You're saying that.
Yeah, in fact, say, yeah, so if I get K, if K is a pure 1 state, I get 0. If K is a linear combination of 1 and 2, there are cross terms where on the left I have 1, and on the right I have 2, and then A dagger 1, A2 picks up a non-zero value. Okay, in some units it gives you 1, right? And you're, can I write that word? So remember, so let's write alpha as cos theta 1 plus sine theta 2, right? And now I ask the question, right? The ensemble average will contain terms of this form, A dagger 1, A2, alpha. So you can immediately, so if I plug in, right, there will be a term like this, cos square theta 1, A1 dagger, A2, 1. And this is 0, right? Because I anti-commute things. I mean, clearly, I write 1. I mean, the intermediate step is that I write 1 as A1 dagger, the vacuum, and so on. Then I use anti-commutation, and I get 0. Then there will be, so the crucial thing, if I have the cross term, there will be a piece that goes like cos theta, sine theta. Most likely I get it wrong, but I get now a 1 dagger, A2, 2, right? And now this is going to be non-zero. Actually, you can choose the normalization so that it's actually 1. And so you get a non-zero contributor. But if I have theta equal to 0, in other words, I have just a simple state, mass eigenstate, an ensemble that only contains mass eigenstates, I'm never going to get non-zero value, right? Because I only get diagonal type terms, 1, 1, or 2, 2. No. Sorry. The statement is you need the thermal bath has to have states that are. The thermal bath is an incoherent. I mean, this P sub k, the weight reflect our ignorance about what's in the thermal bath. But suppose now that the thermal bath contained only, if you knew that it contained only mass eigenstates, okay? Then a mixed term like A1 dagger A2 would give you 0. No matter how, what the weights are, P sub ki, you always get 0. So the only way to get A1 dagger A2 non-zero is that if the states that appear in the thermal bath contain these cross terms. I mean, the cross terms I just discussed here. Think about this in the limit of theta going to 0, right? theta goes to 0, I only have diagonal term.
I get that argument. So that means that your use of the word coherence here is not the coherence that I hear when we are talking about pure state versus a mixed state.
It's more, so the,
Coherence just means that a state in your ensemble consists of a sum of one of your propagation states and another, right? If your ensemble just consists of states that are all propagation states, right, then you don't have this, and that's incoherent. But if your ensemble contains states that are SEMs like this, then that's what's called coherent states.
You need to have coherent superpositions of mass eigenstates.
yes, mass eigen- this would also, I mean, to confuse you a little more, this depends also on the choice. I mean, this, because I'm, as Alexi pointed, so keep always in mind, these are the mode operator for the mass, for the propagation state, the mass eigenstate. If I change basis, it would be the other way around, right? If I use the A, well, there's no consistent definition, but if I use the A, if you change basis for the A, the coherent, I mean, the form of this matrix, the elements are basis dependent. So I could go to a basis where it becomes back diagonal, right? But that means, so within this basis, we're working with the mass eigenstate basis. If I have an off-diagonal terms, A dagger 1, A2, it means that the thermal bath contains linear states that are linear superposition of the two propagation eigenstates, 1 and 2. But the physical thing is, think about the neutrinos, right? Thermal bath contains nu E, right? Nu E are a linear superposition of 1 and 2, or however many neutrinos you have. And then if I go in with A dagger 1, A2, I will get all these cross terms. And if okay, so does that clarify a little bit? Should I go on? So this was coherence of states of same helicity and different mass. But now I mean, so now it's clear what the other terms will mean as well. So if I go off diagonal in the helicity, so if I stay diagonal in the mass label, and I go off diagonal in the helicity, I go left, right. This signals quantum coherence between states with same mass and different helicity. This again, should be familiar, well, not familiar, but it's a case of spin 1/2 particle in non-relativistic quantum mechanics. I mean, there's just, there are the two, you learned, right, that there are two spin states, and if you make it a coherent superposition of the two, and you were to describe it by a density matrix, you would have non-zero off diagonal in that case. So this is familiar from one flavor of physics. I mean, just the electron, let's say, even the electron. And then finally, there's one more generalization when both of them are off diagonal, Ij and HH prime. This signals quantum coherence between states of different mass and different helicity. All right. So, but you see, the reason I was stressing this, once you understand this one, which is the simplest in the context of neutrino physics, then everything follows. It's just a simple generalization. So, okay, so now that we have these are the key dynamical objects, we can collect them into a big matrix of densities, which has 2NF times 2NF. NF is the number of flavors or number of mass eigens. If active neutrinos in the standard model, as far as we know, it's 3, so it's 2 times 3, so it's 6 by 6 matrix. And I have 1 for neutrino, 1 for the antineutrino. And I label that, I mean, L, remember, is the helicity, and here I'm suppressing the flavor indices. So each of these blocks is a 3 by 3 block, okay? This is diagonal in helicity and off diagonal in helicity. Each of them has diagonal and off diagonal objects in flavor, entries in flavor space. So these are NF times NF blocks describing the density of active states, which are the left-handed neutrino and right-handed antineutrinos in the standard model. And these are NF times NF blocks describing the left-right coherence, which in the for neutrinos, Dirac neutrinos in the standard model really means active and sterile states, because the right-handed neutrino has extremely weak interactions in the standard model. In the limit of mass going to 0, it doesn't interact at all. Okay, so that's a Dirac case. In the Majorana case, if you remember, right, there's this self-conjugation properties that you can choose A to equal to B. So you don't need the two 6x6 matrices. You just need one, because basically FRR is equal to F bar. And then we call the off-diagonal, the left-right coherence, we called it phi in the paper. So basically, in the Majorana case, you have one 6x6 object. The 3x3 blocks describe neutrino and antineutrino coherence in flavor space, and then 3x3 blocks describing the left-right coherence, which for Majorana neutrino means neutrino-antineutrino coherence. It's just underlying its spin coherence, but it's kind of, it means neutrino-antineutrino for the Majorana case. All right, so one little more thing about this. So here, all the discussion is presented in terms of these mass bases, because those are the propagation modes. But we can also work in the flavor basis once you know how to go from one object to one basis to the other. And in particular, there's a unitary matrix you can write that relates the neutrino flavor fields to the neutrino mass fields, local mass fields, puts the propagator in diagonal form, and then similarly, from this definition, you can work out how the flavor basis and mass basis density matrices of density are related. I mean, this is just a simple thing. So what are the QKEs? The QKEs are nothing but the evolution equations for these Fs. All right. So that's, and once you know them, you know a great deal about your neutrino ensemble. So do I have 10 more minutes? Yeah, probably yes. Yeah. Okay, so so in the remaining 10 minutes, I just do. Stop at a convenient place. Yeah. I'd like you to tell you a little bit about our approach, how to derive the QKEs from quantum field theory. And again, so hopefully the physics is clear that we need to know information about this one particle correlations, that it's encoded in these matrices of densities that I call F. The idea, how do you write the dynamical equations that evolve F? You start with F's at some initial value or some boundary value, and then you know what's going on later on in the dynamical evolution. How do you do that? One way to do it, which I like because it really leaves very little room to ambiguity and guesswork, is to start from quantum field theory. Basically, you write the equations of motion for the the two-point function of the neutrino in any basis, basically. So alpha and beta could be flavor, and I and j are spinor indices. So you take the neutrino field at point x, nu bar at point y. You take, again, the ensemble average. You do a lot of manipulation that I'm not going to describe. And then you end up with kinetic equations for the f's. But the connection is kind of obvious, right? Remember, nu and nu bar are expanded in terms of creation and annihilation operator. The two-point function will involve, the ensemble average of the two-point function will involve these kind of objects. And those are, by definition, our f's. So if I know the evolution equation, the equation of motion for this Green function, I know the evolution equation for the f's. Cartoonish way of doing this is to write basically the Schwinger-Dyson equation for these two objects. So this two-point function, in the interacting theory, is given by the free two-point function plus this this diagram, which has the free is a convolution of the free two-point function, the self-energy, which is the sum of all the diagram I can write where a neutrino comes in and a neutrino comes out, and they cannot be cut. These are one particle radius that can't be cut, separated by cutting a neutrino line. And then this is again the full propagator. This is an integral type equation. You can transform it into a sort of Dirac equation by acting with the Dirac operator on both sides. Okay, and then it starts looking like an evolution equation, and then you do manipulation and so on. So the details are in the paper. What I want to say is that sigma now is again computed in terms of propagators of the neutrino and propagators of whatever particles the neutrino interacts with, like electron, neutron, depending on your environment. So sigma knows about the environment, knows about, as Baha was saying, there's a contribution from sigma that gives you the potential, tells you that the neutrino now, instead, when it moves in medium, it feels a vector potential. Here I wrote the scalar part, which is, again, proportional to the strength of the interaction, G Fermi, and as Baha pointed out, the density of whatever particles are in the medium. There are also contributions to sigma that characterize not the forward propagation, not the refractive index, but just the inelastic collisions, okay? And again, these are now second order in the weak interactions. They go like G Fermi squared, and then by dimensionality, you can have either temperature to the 5th power or density times temperature to the 2nd power, and so on. There are a bunch of contributions, depending on the physical situation, all right? So this is just, again, a way to say in words how to go from the full equation to the kinetic equation. The details are not important. What's important is what approximation go. How do we what physical assumptions go into this arrow, going from here to here? And let me spend a couple of minutes on this. So we do exploit, in going from here to here, a hierarchy of physical scale. And in particular, work to second order in these small ratios. And let's go through this hierarchy of physical scale. We're exploiting heavily the fact that these are, if E represents the typical neutrino energy, which is in non-degenerate system goes like the temperature, essentially. So we use heavily the fact that in the environment that we are interested in, neutrino are ultra-relativistic. So small neutrino masses. We also use the fact that mass differences are small compared to the typical energy. All right. We also will use this power counting that for compact objects, the external potential, the medium and neutrino induced potential, are comparable to delta M and Mn. This is not the case in the early universe. In the early universe, this is much smaller than these other quantity ratios, but in the compact objects, this can be comparable, so we count it of the same size, and we keep all the terms. All right? And then we assume that, of course, we live in a background that could be the supernova envelope, could be the expanding early universe. There's also another small ratio, which is the dx over the energy. So the backgrounds are varying very slowly compared to the scale of 1 over E, all right? And this is, you can check in case of the Hubble time, and also in the case of scale height for supernovae. I mean, these are macroscopic lengths or times compared to the E or 1 over E. And then there's again, there's also the effect of inelastic interaction. And this, it's kind of intuitive. It comes to second order weak interaction. So you count it as epsilon squared. If we counted this one as epsilon, we count the inelastic. So the potential is an amplitude. The cross-section for inelastic scattering an amplitude squared, square modulus integrated over the phase space, so we count it as epsilon squared, right? So these we heavily use, all right? Otherwise, this set of equations, it's impossible to solve, to handle, all right? So, and the physics, again, let me just, if you look again at the physics is the physics of ultra-relativistic that we use a lot, and then it can be summarized as this, that the oscillation length, which goes like E over delta M nu squared, the mean free path, the collisional mean free path, and the length scale associated with the external gradients is much larger than the de Broglie wavelength of the neutrino, which is 1 over E, 1 over T, okay? So that we use heavily, all right? And there's one, so for those of you who are a little more formal and they ask, oh, what about this ensemble average here? The initial density matrix of the system. So where does it end up? When we end up, so this equation, the QKEs are differential equations, right? We write differential evolution equations for the Fs. What happens? Does the system retain memory about the initial density matrix of the system? And the answer is yes. That shows up as an initial condition for your differential equations, or a boundary conditions if you go to a kind of a static thing. So everything seems consistent in this approach. Let me again advertise once more why I like it. I particularly like it. So the advantages. Well, this of course it's new in the context of neutrinos, but it had been used already in other contexts, such as baryogenesis in the early universe. So the advantages are that this is a first principle method, and so it's basically forced us, for example, to think about left-right coherence. So when we looked at the component, we knew, right, that, okay, we want to write equation for the two-point function, and we were getting some extra terms. The decomposition of this two-point function had some ugly term that we did not, at first, we did not know how to interpret. Then upon thinking a little bit, we identified them as the spin coherence, the left-right coherence. So we were kind of forced into this by the method, and which was good. There was no guesses or fudging. So a bunch of if you know how to compute diagrams, Feynman diagrams in non-equilibrium quantum field theory, then you know basically all the terms in the QKEs with the exact coefficients in front. You don't have to guess or anything. And then, last but not least, we have a systematic, in principle, improvable set of approximations based on this power counting in the epsilons, on this ratio of scales again. Here we are borrowing from ideas in effective field theory, which is basically expansions in widely separated energy or length scales. And maybe, yeah, 1 minute. So after all this, so this is more than 1 year worth of work. It's basically all went into Alexis' thesis. I think it's a monumental thesis. So here's what you get. Again, remember the Fs are 6 by 2NF by 2NF matrices. In the general Dirac case, you have 1 for F, 1 for F bar. And let me walk you through the structure, and then tomorrow we'll look into details at each of the terms. So of course, this is in the simplest case is the time derivative, but in the general case is the derivative along the neutrino word line. It contains the time derivative, but also a drift term like the v dot d in the x term, and the force term, which is p dot time d in the p. We'll go into detail tomorrow. But these are sometimes they're called the Vlasov term or the Liouville term. So this is the evolution along just a coherent thing along the neutrino word line. Then you have a commutator with an effect, Hamiltonian-like operators that encodes the vacuum mass evolution, the mixing due to vacuum mass. These are, again, H is an off diagonal. There's all components. It's a 2NF by 2NF matrix commuted with F or F bar. It contains vacuum mass and forward scattering, refractive potential. This is the MSW term that Baha discussed already earlier on. And finally, there's a Boltzmann type term. There's a collision term that, again, it's a matrix structure. It encodes, it tells us how the evolution of the Fs is affected by the fact that, let's say, a neutrino of momentum p can scatter into a neutrino of momentum p prime. And in doing so, it can also change flavor. All right? So there are, actually, it can change mass label. It cannot, so we'll discuss it tomorrow. And so this is a generalization of the Boltzmann term. All right? So this is the structure. It's intimidating, but hopefully, by now you know the physical meaning of all these things, the Fs at least. We'll look at the D, H, and C tomorrow. But so F, H, and C are 2NF by 2NF matrices. The equations are a monster because all the components are coupled in general. So computationally very demanding. they're highly nonlinear because D, H, and C are functionals of F and F bar, right? So I'm sure earlier in the conference you've learned that the neutrino-induced refractive potential is a function of F, of the neutrino flavor composition. So even this innocuous coherence term is a highly nonlinear problem. But then C, obviously, the collision term, know about F and F bar. They know how many neutrino you have. You know, the loss term is proportional to F, how many neutrino you have. The gain term is proportional to as the Pauli blocking factor, identity minus F. So it's a mess. It's a challenge, should be a challenge for you guys. And finally, just a comment about this. Because this is obviously hard, if you look at search through the literature, the state of the art is the following. In the early universe, you obviously have these two terms. The inelastic collision are drastically approximated by some damping term, which doesn't couple. It's a diagonal, let's say, in a momentum space. It's definitely inadequate for the decoupling regime. It's basically near equilibrium approximation here. When we're going out of equilibrium, there's no consistent numerical solution analysis, computational analysis of this. For supernovae, as I said, there's two regimes typically. So in the inner core, so probably the supernova modelers, they neglect completely this one. In the inner core, they reduce this set of equation to Boltzmann type equation and do Boltzmann transport for unmixed neutrinos. And the collective oscillation and MSW folks, they neglect this in the outer low density regime, and they do the coherent evolution here. And of course, so there's no simultaneous inclusion of both terms. And of course, everything, actually everything is confined to the upper 3x3 block. There's no inclusion of spin degrees of freedom. It's treated as a NF type by NF problem. Okay, so hopefully this sets the table for tomorrow. Tomorrow we'll look a little bit into the details of what and the physical meaning of D, H, and C. And I will stop here.
So this fits very nicely, actually, if you really want to get into this. It fits very nicely with what Baha talked about yesterday morning, right? So, questions?
Yes.
So you mentioned a number of times the difference between if the neutrinos were Dirac fields
Yes.
and Majorana fields. So at this point we have no idea which one it is. Like.
So yeah, it's an open question. So most theorists have the prejudice that they ought to be Majorana, but there's no experiment. So there is one way to test this. So if neutrinos are Majorana, the mass term that you can write basically violates total lepton number. All right. So there are processes. On the other hand, in the Dirac case, the mass term does not violate lepton number. So there is a very clean signature. Well, you can say, okay, I'm going to look for lepton number violating processes. I can look at it at Collider. I can look in low energy processes. The deepest probe is something called neutrino-less double beta decay, where it's a second order weak process where basically in terms of neutrons and protons, you can think of it as two neutrons going into two protons and two electrons through a double beta decay in which the neutrino, however, becomes an internal line and is not emitted. There's no real neutrino emitted, sort of virtual neutrino. That line can close into itself only if lepton number is violated, therefore only if the neutrinos are Majorana. So there's actually that's a big investment in nuclear. This is expensive experiments. There are several searches ongoing in the US, in Europe. That's one way to determine experimentally. But we don't know yet. I mean,
So if it was a Majorana, then it would be the mass eigenstates that would be Majorana particles, or even the flavor.
The question is ill posed. I mean, it's just the.
I thought that we could distinguish between like electron neutrino and anti-electron neutrino in some detectors, so they couldn't be like.
Oh no! In that case, what we call the What they call the anti-neutrino is just the neutrino with the opposite spin. I mean, it's
So those are the weak interactions.
the weak interactions.
They, obviously they determine how the neutrino interacts weakly. So that's different from the energy eigenstate, the mass eigenstate.
Right, so yeah, that's what I meant.
Yeah.
So the mass eigenstate, like nu1 would be the same as nu1 bar.
Oh yeah, in terms of fields, yes, you write it that way. Yes, but the self-conjugation property you impose it on the mass. Yeah, well, the only thing you know how to quantize is when the mass is diagonal. So you go to harmonic oscillator, and yeah, you have to go to the diagonal. Sorry, yeah.